name's Tom Hayden. I'm Solenis Global Market Director for our Virgin Pulp Group, and I'll be facilitating today's call. Before we get started, I'd like to cover some basic housekeeping items. The webinar is being recorded and a copy will be shared on solenis.com. We do request that people please mute their phone lines during the presentation to minimize background noise. However, there will be time for Q&A following the presentation, and if there are questions during the presentation, they can be asked in the chat window. With that said, let me please introduce our speaker. Dr. Michael Wang possesses several degrees, including a PhD from North Carolina State University in Wood and Paper Science. He has over 40 years experience in the pulp and paper industry in a variety of roles, including research, teaching, and process development. He's published over 20 papers and is the owner of several patents. Dr. Wang will be taking us through his presentation on best practices for controlling scale in a bleach plant DO stage. So at this time, I'll hand it over to Dr. Wang.
Good morning or good evening, everybody. Thank you for you taking time to attend this webinar. We are going to discuss skill control best practice in a bleaching plant D0 stage. This is the agenda. We're going to go through ideal condition for D0 stage in the multiple bleaching sequence, and the effect of pH on chlorine dioxide delignification reaction, impact of raising D0 pH on the scale formation, and compare between calcium oxalate and barium sulfate, minimize scale through process optimization or modification. Then we're gonna talk about situation you may need using a skill control program. Then we're going to present present skill inhibitor on the market and some, at least two case history. Then we're going to conclude with industry best practice. So as you know, traditionally, we're using chlorine water in the first stage. That time, the condition pH around 2, pH pulp consistency 3%, retention time around 30 minutes, the temperature is below 50 degrees. So at this lower pH, the most metal one gonna remove under, during washing. So not many mills has a scale issue in the D0 stage. So we know later 1990s, majority bleaching plant remove elemental chlorine. So now substitute or replace with chlorine dioxide. So the chlorine dioxide and chlorine is a different chemical. So we got to change their condition. So the pH now we're using 2.5 to 4.5. Pulp consistency 10%. Retention time 30 to 80 minutes. The temperature, 70 degrees. Since we're raising D0 pH, there's less metal ion gonna release from that stage. So they're gonna carry over into D0, the forward. So they're gonna cause more issue. So this is the reaction. I will not go through all the detail, but I just want you to pay attention. At a different pH, we have a different reaction taking place. So all those reactions associate with delignification. So here's some summary. So no matter what the pH you start with, 1.5 or 2.5 or 3.5. So in the system, you always have chlorine dioxide, hypochlorite acid. You also have a hypo and have chlorine. So different chemical, they have a different reaction. Like chlorine dioxide gonna react with both phenolic and either fied unit. So what that means is they're gonna have more lignin removed. So chlorine delignification is through substitution and oxidation. In the high pH above 4.5, then fuel generate chlorate. The chlorate react only with free phenolic, then very slow. So when the oxidation, contribute very little to delignification, but just the brightening. So that's why this is stage we want to have delignification, then we need, right pH. So this is the people study, like Peter and Cornell. They did 2 different softwood and hardwood. If you look at for delignification, should be, both in 2.5 to 4.5 around. So this is for both hardwood and softwood, apply. So when you increasing D0 pH, there's some changes, especially related to scale component. So the calcium solubility greatly reduced when the pH increasing to 3.5. The calcium and barium is very hard to remove during D0 stage washing. So also oxalate ions concentration gonna increasing because through the pH change and equilibrium. So if we increasing pH, to a higher level, then you're gonna have less sulfuric acid needed. So then the sulfate ion is gonna less. That point the higher pH gonna fuel less barium sulfate. So some of those microcrystal I was distracted. Some microcrystal calcium oxalate, if not deposited, which is the particle size too small, they may carry over to extraction stage, then convert to calcium carbonate. So this is a pH change the scale component. If we look at here, if we talk about calcium oxalate, if below pH 2.5, which is this part, you don't have much oxalate. But when you increasing pH, you're gonna generate a lot of oxalate ions to making scale formation possible. So for sulfuric acid, if you get a 2.5 somewhere around here, but you still have some. But if you get a pH higher, even you generate more sulfate ion, but you don't have much sulfuric acid in the system. You don't need it. So what to making, get those each skill component in the process. So we're gonna compare those two. So if you look at the major calcium sources in the wood, especially bark, so we're gonna have 2,000 to 6,000 ppm for hardwood and 1,000 to 4,000 for softwood. But on the other hand, the barium sources from wood are, much less. So hardwood you have 20 to 60. Softwood you're gonna have, like 10 ppm. So if you are making a skill, formation, then you have to have the both concentration to reach super saturation point. Because the barium is so small, the majority contributions really come from sulfate. So that's why we care D0 pH. So if you look at, the sulfate sources, they're mainly using for justify D0 pH, and the sulfur compounds which carry from boron stock. Those sulfur compounds are going to convert to sulfate, and white water contain alum also can contribute sulfate. But for oxalic acid, basically come from bark and oxidation lignin. So there's a number of studies indicate every 1 carbon number reduction, 1 kilo pulp, you're going to generate about 80 gram oxalic acid. So since both calcium and oxalate has a higher concentration, but this is both sometimes, major contribution to the skill. But for barium sulfate, as we discussed, the sulfate ion is the key to control barium sulfate. If you're raising pH, you're gonna have less sulfate. So from KSP solubility products, so we're gonna see calcium oxalate are gonna be 10 times higher than barium sulfate. So if you form any of those skill, you change condition for calcium oxalate, you may dissolve back. So that's create a chance to build up those skill components in the process. But for barium sulfate, it's very hard to dissolve again. So basically, if you form the skill, then stay there. So for the system, if you only have calcium oxalate, you certainly can drop the pH to 2.5 or 2.8. That way, you can reduce or eliminate the skill. For the system only have barium sulfate, you can increasing pH to 3.5 or 4. That way, you do not need much acid, which is sulfate concentration is going to be really low. So those metal ion associated with the fiber also have a different infinity. This is the order. So basically, the calcium much easier to release from fiber compared to barium. This is the study people to show, the carbon number reduction gonna increasing oxalic acid. I just want to mention the bottom. This is a peracetic acid. So basically, they're gonna oxidize the further oxalate acid, to carbon dioxide. That's why it's not really go up, it just level off here. This is from another angle to look at each stage, how much oxalic acid generate. So we can see the oxygen delignification create most oxalic acid. So D0, which is the first stage of bleaching, also producing a dramatic amount oxalic acid. Then as the carbon number reduce, then gradually, you don't have much oxalic acid generate. So we know we have this information, then we know if we can modify our process. So we're going to be much less skill formed, which is a lot of cost effective compared to using any skill control. So the first one, we really need to control bark content. As we discussed, if you have bark, you're going to have all the metal ions, plus you have oxalate. This is a carryover to the process you hardly to remove, even you can, but it's a really great problem for the washing. Second, we need to improve brown stock washing, reducing those metal ions, reducing caustic, reducing sulfur containing compounds. Why caustic is matter? Because if you get a stock has a higher pH, you need more acid to neutralize. Those acids basically carry sulfate into the process. Then we need a lower D0 pH to 2.5 or 2.8 to eliminate or minimize calcium oxalate. If we have barium sulfate, we need increasing pH to reducing sulfate concentration. So we also can monitor the process, especially filtrate, to see how close to the supersaturation point. If they are close to or past, we can purge some D0 filtrate, instead of using some fresh water to avoid any metals ions build up. We also need to avoid controlling D0 pH with span acid. So we also don't want to run concurrent washing in the bleaching plant. So then we do not want using white water contain alum. So this is calcium oxalate a chart we build up. You can look at how much oxalate concentration and how much calcium concentration. You can actually looking for where the supersaturation point. If in this dark region, you may have potentially to form skill, then you need purge some of those filtrate out. So even we can eliminate or reducing skill through process optimization. But in some of those situations, we cannot completely eliminate. Then we need to using skill control. The first one is really when you have both calcium oxalate and barium sulfate. So you cannot satisfy both by increasing pH or drop the pH. So the second is really the mill using too much caustic acid, you have justified pH, which is, bring up, then you can reducing caustic, reducing acid usage. Also, some plant have limited capacity to producing chlorine dioxide. You want to improve chlorine dioxide efficiency by bringing pH up. So we talked about earlier, what the pH for delignification is better. We also need limited water, especially some of those reusing or recycle water containing high calcium and oxalate ions. Because some mill, it just does not have water sources. They have to. I know a few plants, they run concurrent washing. So some of those mill has so rapid skill formation to cause a quality issue, or they need to frequently shut down loss production. So, and also some of those skill location taking a long time to clean up. We would rather to using skill control to push the skill down to the stream. Some location easier to clean up. So all those situations, we may need to consider skill control. But every time when we talk about skill control, people start, saying, do I need spend more money for those skills? The answer is no. Actually, the skill control program should pay itself, and also same time has saving for the mill. So the following is present market skill control products or chemistry. So we can look at, lower pH, every chemical performance well. But when you raising pH, especially for calcium oxalate, some of those mill has neutral pH, 5 or 6. So if you look at how much you dose compared to pH 3 and pH 5, you're gonna using like how many times? This is like 80 times. So basically, you cannot afford to using those chemicals. This is why our products is really making a difference. Okay, I'm gonna show you 2 cases here. The first one, this is basically the problems. They have both barium sulfate and the calcium oxalate. So they need to clean up every 2 weeks. So the pH run about 2.5. So then we're gonna change. We change the pH to 3.5. So we save acid. You can compare. This is 11 pounds per ton reduction. We also saving chlorine dioxide. This is close to 5 pounds. So original, every shutdown the mill had to boil out, but now we'll do every other time. So also the production increase. So if you put all those together, it's really a lot of saving for the mill. The second case, this is about 1,600 ton per day craft softwood and hardwood mill with 5-stage bleaching. They using kiln to boil out every 2 months. So then the skill create those downtime and also have a safety issue. So the mill wanted to apply a skill control program, then we did. So the benefit is really we're reducing kiln to boil out from 5 to 6 times a year to 1 or 2, basically from 2 months to 6 months. We're reducing 1.5 kilos per ton of chlorine dioxide and 3 kilos per ton sodium hydroxide. The mill actually purge some filtrate to remove calcium ion. So ROI for the program is over $1 million. So we gonna using the best practice to conclude this. So the first one, we really wanted to control bark less than 0.5. But for the southern mills, there's no issue. But northern part, especially during winter, you can have a lot of ice and snow, and the bark cannot come off from the log. So improve washing to remove sulfur compound, caustic, calcium, and barium. Lower pH, if you only have one skill with calcium oxalate, or you can raising pH to 3.5 to 4 if you only have barium sulfate. So avoid the control D0 pH with spent acid from chlorine dioxide plant. Raising D0 pH to 3 to 4 to save chlorine dioxide and caustic and acid. But some of those mills, we only increasing, 0.5 or 0.6 pH unit, which is from 2.5 to 3.2. So they save more than 15 pounds caustic. They also save chlorine dioxide. So monitor the skill saturation point by purging some filtrate partially to remove calcium and oxalate. Avoid running concurrent washing, and also using anti-scalant program, which is skill control, when the skill cannot be eliminated with the process modification. The program also provide a huge ROI and have enough saving to pay the chemical itself. So you don't have to have extra budget. That's all the presentation slide I have. If you get any question, I would like to answer.